All right, we're good. Milo, how are you doing?
I'm good. Yeah.
Nice. So I just have one big question for you.
Okay.
What is quantum computing?
It's when you make a computer that fundamentally runs on quantum mechanics, and like already, like the computer like you have in front of you that's recording audio, like it's using transistors, and the transistors it uses are using quantum effects, kind of. So it already is like slightly a quantum computer, but in the quantum computers people are talking about when they say we want to build a quantum computer, it's one where not only are the parts quantum, but the way it processes information is quantum. So like you could sort of imagine that all the components on the computer on your laptop are totally classical, and there is no weird quantum effects, and just like you have bits, and then you have like different logic gates that tell you how these bits interact with each other. But on the quantum computer, you can't pretend the world is classical. Like the quantumness is in your face. It's in the way the computer processes information.
Yeah.
It's a quantum computer.
And what's the benefits of that versus having a classical computer?
The benefit is that a quantum computer can do things a classical computer can, and so the way people first made this observation, like there is this famous talk by Feynman, where he was musing in it about how there's these effects and these interactions in quantum mechanics which are really hard to simulate. Right? So you have physicists who have their computers and they're trying to simulate like the way different molecules are going to interact with each other. These different small quantum systems are going to work, and they can't do it. The computers can't simulate it. And so on that one level, this is like a downside. Like this is bad. We can't simulate our physics. This is like holding up scientific progress. On the flip side, you find that this means that quantum physics, these small things we can't simulate, are doing something our computers can't. Right? If our computers can't simulate them, the physics can. Right? Like here's a really quick way to tell how two molecules interact. Just make the molecules help them interact. Right? They're going to interact in some way. You're going to get output. And so in a way, the fact that quantum mechanics is hard to simulate means it's doing something we can't simulate. It means it's doing something sort of beyond classical power. So that's how you know that quantum computers can do something we can't.
Right. And it does that using the qubit, but can you kind of describe in a very first simplistic and then as complex way as you can with a qubit, with like superposition, and I know sometimes people use like some sort of like vector where you get it up or down. Can you describe that?
So if you want to talk about computers like abstractly, you want to make some claim about how computers work, you don't have to talk about bits and how bits interact with each other. You can sort of make general claims like they process information, they take inputs, they spit out outputs. You can say things about computers without talking about bits. And similarly, you can talk about quantum computers without talking about quantum bits, qubits, right? And so the most simple types of computers rely on qubits. Not all quantum computers do. Like the sort of quantum computing I do typically doesn't rely on qubits. And so in my eyes, like a qubit is just a nice metaphor for like the simplest piece of quantum information. Like a bit is like it's either on or off. There's either current flowing through a wire or there's not. And similarly, a qubit is kind of the simplest piece of quantum information.
How powerful are like the most powerful quantum computers right now? Because I know the most powerful classical computers have like billions of transistors in them.
Yeah.
How's quantum looking like?
Well, if I want to say the optimistic number, right, like the PR line, you would say, a couple hundred. Right now,
okay.
A couple hundred. So this is like the most optimistic way of looking at things. But there's an issue, which is that you can't use the qubits we made right now. Right? Like you have like it's a single like unit of quantum information, but like the ones that have a couple hundred qubits, they're stored in these very, very noisy ways. Like for instance, you'll have like some atom, like rubidium. I guess that's an atom. You look it up on the periodic table, and it's stored in the position of a single electron. Right? It's either is it in this orbital or is it in that orbital? It's like which orbital is it? And what is the position of this individual electron? And it's a very, very small thing. It's a single electron. And so if someone like turns on a microwave in the room next door, it'll like mess it up, it'll jump, right? And so the way you protect it is you put it in a fridge, you make it very, very cold, you do your best to protect it from the environment, but it's still noisy.
Yeah.
And so you have a whole bunch of very bad qubits, a couple hundred of them. And so then people do this, this form of error correction where you put in a whole bunch of bad qubits together, and you get a single good qubit out of it.
Okay.
And then, but that process, if you take in like 60, qubits to make one good qubit. And so now your couple hundred turns into 5, right? Because you took a whole divine qubit to take one qubit. And so I would one way of looking at it is with a couple hundred qubits. But if you want to actually look at the logical qubits, the ones you can use for computing, it's like 10. Like it's more, it drops down a lot.
What can we do with like just 10 qubits?
You can learn how quantum computers work. Like people do things and they say, wow, this is what interesting data we're getting. Like we're finding out how our computer works and we're learning more about it that's going to help us build things in the future.
Yeah.
And so physicists care about the results that are coming out of these 10 qubit states. But if you're someone who's like practically minded, you're saying like I have a computation problem, like I run like a finance company and I want to use a quantum computer to crunch our numbers.
Mm-hmm.
Like you will not care. Like no one who has concrete computation problems is going to quantum computers to use them to solve them.
Yeah.
Right. That's not where we're at.
Yeah, I was hearing about the I forget the exact technical name, but then the finding the prime numbers of a very large number.
Yeah.
And I heard that you need about 100,000 qubits for reference to solve a problem like that.
Yeah.
But now we're only working on scales of 5.
Yeah.
Okay, gotcha. And to condense those 100 qubits into 5, is that quantum entangling those 20 qubits into 1, or is that some other process that is allowing that to happen?
It's a really subtle process, and so it's this form of like quantum error correction, right? Like this, how do you take a whole bunch of bad qubits to make one good one? Which is actually like that's what I do. Like I spend a whole bunch of time thinking about these sorts of ways of doing it, because the hope is that like on one side there's people trying to make as many qubits as you can and make them as good as you can. And on the other hand, you have to get better and better at squeezing out good qubits out of it. And so typically like it is some sort of complex entanglement between a large number that makes these like weird wave functions that are somehow more protected from the environment than the individual ones.
And is that where topology comes in?
Yeah.
Is it topology of the wave system? Or is it something else?
Yeah, so like that wave function is sort of described in a way by topology.
Well, how about this? Why don't we start by describing the wave function, and then you can get into topology, and you are more than welcome to go in as in-depth and as complex as you go.
Yeah.
Just have fun with it.
So, I mean, like, what is a wave function? Like, if you describe, like, a bunch of, like, a classical system, right? Like, you describe, like, just, like your position, right? There's going to be just, like, some way of describing it, some way of describing the state of a classical bit, which is the positions of all of its components. In quantum mechanics, things don't have well-defined positions. They sort of spread out as waves. And so if I want to describe you, I don't say all these positions. I say all these spread out or wave type things. I describe your wave function. And so the wave function is how you describe something in quantum mechanics. It's described by a wave function. And so when you have some big complicated wave function, I say it's some big complicated state, right? I could just use the word state. It's just a way for those qubits to be.
Yeah, and so where does your work tie into all of this and quantum computers? Like, what exactly is it that you're researching and doing?
So people have this problem. They find that even when they make thousands of qubits, they only actually get like 20 out because you have to put a whole bunch together. Or even like the original problem, if your qubits are noisy and you don't have any ways of putting them together, you just have a whole bunch of bad qubits. And no matter how many bad qubits you make, you're never going to have a good computer. And so people say you have to solve this. You have to solve the issue of having a whole bunch of noisy bad qubits. And the answer typically is to use a math of topology. And so topology it's a math class. If you are a math major at a university at UC Santa Barbara, you will take it like in your second or third year. And there's a real way in which this math helps you protect quantum information. And so that's kind of a topological quantum computer, a quantum computer you use making topology. And this fits into two major branches. There's one branch which is, let's find some material which is topological in nature, right? So these materials exist and are in a real sense described by topology. And
what do you mean by that? Like, can you give an example?
What it means, so if I want to give you an example, I would say like a sheet of graphene. So there's a bunch of carbon atoms arranged in some flat plane. You make it very, very cold. You pump a huge magnetic field Correct. It's like 5 Kelvin is the temperature, so that's very cold. 15 Teslas, it's a magnetic field. That's very big. And you start getting some weird stuff. Yeah. And that's topological quantum at that level, right?
Okay. Yeah.
And so that's an example. And I mean, before I can describe what it means for something to behave topologically, I'd have to like say, what is topology here in this little math class? But yeah, I mean, when you describe it, it's gonna use that math, right? Like you're gonna need it, and you're gonna use subtle concepts from that math. And so that's topological quantum computing. Mm-hmm. And so either, like I said, it's split into two main branches. One is you find a material, you do like this sheet of very cold, very big magnetic field graphene, and you make a computer out of that. Like this is your computer chip. Like your computer chip is really cold graphene. Yeah. And then you build it out of that. Or and this is kind of cool insight. Okay. You start with a just normal quantum computer. Okay. So you built it, you have a whole bunch of bad qubits. What can quantum computers do? Quantum computers can simulate quantum systems. They can simulate other quantum systems. You use your bad quantum computer to simulate a topological quantum system. Okay? You simulate a topological quantum system. Topological quantum systems are resistant to errors, like I just said. Like that's how you build them. And because you simulated something resistant to errors, you become resistant to errors. It's like Kirby who eats someone else to take his power. It's like you simulate the topological system and you become error resistant. You inherit that. Yeah. And so that's what you do. Like, and so like on all your qubits, like in this all your rubidium atoms of their electrons in different levels. Like you're simulating what would happen if you're on a graphene sheet at really low temperatures and high magnetic field, and you're stealing its error resistant properties. Mm. And so, from a physical perspective, these are very, very different processes. For a mathematician, it's like, well, mathematically, it's the same thing going on, right?
Yeah. No, but the simulation has limitations, right? Yeah. Because if you only have 5 usable qubits, then I imagine you probably can't simulate 10,000, right?
So, what's cool is the simulation is not being done with the 5 usable qubits. The simulation is done with your bad qubits.
Oh, I see.
And the point is, when you simulate the system, your qubits become good qubits because your big system built out of bad qubits will simulate a smaller topological system, and so the smaller topological system is going to have 5 good degrees of freedom, which are actually protected from errors. Yeah. And so that's how you do it, and so you can really simulate big topological systems with a whole bunch of noisy qubits.
Yeah. Yeah, so this is what you're going to CalTech for next year, right?
Yeah, so I'm going to grad school at CalTech I guess I'm in the math department, but my advisor, he's taken 2 physics students before and 1 computer science. So it's never taken a math student. Mm-hmm. So it's really taking mathematical physics, thinking about how does information work in these topological quantum systems.
Yeah, and is it, like, do you do a lot of coding, like, with your work, or is it mostly just kind of pure mathy in that sense?
What people talk about, like what's coding is subtle, right?
Okay.
So if you want to program something on a quantum computer, at the current level, you're going to have to specify like a bunch of rubidium atoms with electrons at different levels. Like what are their positions at different moments? Like you have to like rotors moving those around. Mm-hmm. Like where exactly do you want to move them? And then you're also going to specify like you're going to be like shining lasers at them to implement quantum case. Like how strong do you want your lasers to be? When do you want to time them? Like, it's a really concrete process. It's really very, very grounded process, and there's no high-level programming language for it. And the reason you don't have a high-level programming language is that every month the computer changes, and so you have to rewrite the language, and there's no point. Mm-hmm. Right? So it's very, very tough thing to do, and it's a very expensive experiment to do it. And so every time you kind of run a new error correction algorithm on one of these computers, this is a big endeavor, and you like get a paper out of it, right? Mm-hmm. So it's like every time that you write up your code, you like publish it and say, look, I coded this thing. Yeah. And the fact that you coded it and it ran as expected, it's like, is the result that you're publishing? Yeah. Right. So in some sense, like I'm part of this coding process, like I'm part of coding a quantum computer, but like I'm on the more abstract side. Mm-hmm. Like I haven't done any sorts of experiments yet, but one of my colleagues who was at CalTech, he's a postdoc, Nathan and Tantisavadakarn, he went to some lab and said, great, I have a new error correction algorithm that you simulate this specific topological quantum system. You should let us do it. They said, great, let's do it. And so then like they got a group of like 30 people together, and they spent like 6 months, and then they simulated it, and they saw that it sort of worked, and then they got a paper, and so they all kind of worked together to code it.
So being on the more theoretical side, are you working a lot with like the quasi-particle that makes topological quantum computing work? Is that...
Yeah, so here what you're referring to is the fact that there's these things in topological quantum systems called quasi-particles. And so the word quasi and quasi-particle means that it's something that behaves like a particle, but is built out of a whole bunch of smaller degrees of freedom. So for example, like a wave on the ocean it's not a bunch of water molecules moving, right? It's a whole bunch of molecules going up and down all at once. But you have this sort of emergent thing, which is a wave moving. Like you say that's a wave, like which water molecules are in it is changing all the time, but it feels it's this emergent thing that moves. And similarly, quasi-particles are built on a whole bunch of smaller things, but you see it as like this bigger thing coming out of it moving around. And so this notion of emergence is kind of, in a way I'm already talking about, like when you have a whole bunch of noisy qubits that go to make a few really good ones, that's emergence, right? Like you have like one good like little wave being built out of a whole bunch of noisy molecules.
Gotcha.
And like you can see down the ocean, like if it's a really rough night, your water is sloshing up and down, you have a whole bunch of really noisy water. But the big wave is moving at a nice constant, right? That's even in the storm, that's clear. And so that's how what you're making. Like you're in a storm, which is the environment, and you're getting that big wave out of it. And so that's the emergent property.
And that's how you're able to work with something that doesn't really exist in some sense, right?
Yeah, because it's built out of all these, and you see it.